transform analysis of discrete time LTI system. So this particular, what is meant by this transform analysis? So let us see. Let us see. So we know that given the input and the impulse response, if at all we perform the convolution, we get the output, right? So what is it? If at all you happen to know the impulse response, then if at all any input is given to you, deterministic input, then its output can be determined, right? So now if at all I take the Z transform of this thing, if at all I take the Z transform, then H of n becomes H of Z, X of n becomes X of Z, Y of n becomes Y of Z, and the convolution becomes multiplication. Now that's a big deal. Okay, that's a big deal in a way that if at all we happen to know the input, right? Say you got this black box. If at all you got this some black box where you don't know what this box does, right? Where you don't know what this box does. Okay, what this box does, right? Then what you can do, you can give different types of test inputs. Okay, different types of test inputs, and you can observe their output. You can observe their output, then afterwards take the Z transform of the output and the ratio of the Z transform output divided by input. That will give you the transfer function. Then you take the inverse, then you take the inverse of it, then you take the inverse of it. What do you get, by the way? Then you take the inverse of it, you get the impulse response. Then you take the inverse of it, you get the impulse response. By the way, was it such a difficult task? Was it such a difficult task? See, the whole division thing, the whole division thing is not possible in the time domain. Okay, whole division, because this is not multiplication, this is convolution. So the process, yes, there is a process. Okay, if at all you happen to know the output and the input, there is a process, there is a process to know the impulse response. It is called as actually deconvolution. Deconvolution is a very tricky task. You can see in an entire textbook there are only one or two problems available. It's a recursive process, it's a recursive process. Okay, so that is why doing the transform way is always much easier and much clever. Okay, so the transfer, okay, the transfer function, sorry. So this H of Z here is called as the transfer function. So what is the transfer function? The Z transform of the output divided by the Z transform of the input. And what utility does it give? Why are we interested in the transfer function, by the way? You have a similar transfer function, right? The H of S, right? You might have seen there is a similar transfer function H of S, but that exists only in the Laplace transform, right? That exists only in the Laplace transform. Okay, now let us see. Okay, so are we clear here? So what is a transfer function? If at all you take the Z transform of this entire equation, you get the ratio. Now the ratio of the output divided by input is the transfer function, and if at all you get the inverse of it, you can always get the impulse response. So handy tool, because the deconvolution, the so-called very complicated iterative process, will be converted into simple division. Okay, let us see what are the utilities of the transfer function. Why are we interested in this transfer analysis? I'm just going little away from your topic here. Okay, so now let me just relate the actual circuits or the actual applications with the thing. Okay, so I wanted to tell you what actually is a difference equation. So I understand that in your mathematics, I don't know whether you have studied difference equation or not. Okay, so if at all there is a normal analog circuit which contains some inductors and some capacitors and supply, then if at all you try to represent in terms of voltages and currents, you end up getting the differential equation, right? You end up getting differential equations where these numbers, right, indicate the values of the resistance or the inductance, and the order indicates what is this order indicate? To indicate there are two memory elements here, and so on. Similarly, if at all there is a digital circuit, if at all there is a digital circuits, in the sense, what sort of circuit we are talking about? Moving average. How the you are currently, what is your average now that you are in fourth semester? What is your average? Your average is current semester marks plus previous semester marks, right? N minus 1, let me call it n minus 1 plus marks previous to that semester. Okay. Last 3 semester marks, they consider n minus 2. Then whole divided by 3. Whole divided by 3 means this into 1 by 3, this into 1 by 3, and this into 1 by 3. So don't you think we will get this kind of application? See here, I am manipulating on the digital data, right? The discrete data, your semester, this semester, previous semester, semester previous to that. And what you are doing is you are giving a delay, right? Current semester, previous semester, and semester previous to that. So this particular operation can be represented, moving everything can be represented using a digital circuits, where these elements here, these indicates the D flip-flops, one flip-flop, one time unit delay. And these things here, they indicates the multiplication by certain coefficient. So here you can see B0, B1, and B2. There are three: 1 by 3, 1 by 3, 1 by 3, and this delay. X of n, this is x of n minus 1, further n minus 2, and n minus 3. Okay, got the thing. So we end up getting so called the digital difference equation. So there we have it. We have something just like we have the differential equations to represent analog circuits. So here we have something called as the difference equation to represent this kind of digital circuits. Okay. So now can you relate, by the way, differential and the difference equations? Okay. So y of n is equal to x of n, the current value of n. Sometimes it so happens. So now you can see here the output y of n depends only on current input and the previous inputs. It need not be previous input. Sometimes now your Shivanand sir teaches you this control system, right? Control system with feedback. Sometimes it so happens, you have seen this counters, right, where you can see you have the input and your output will be fed back to the input, right? Say there is a feedback also. Here this was a simple case, right? There was no feedback, so your output contained only inputs and its derivatives. Whereas if at all you have a system, there can be a system where output can also be there, right? So there can be output also. In this particular case, what's going to happen is, see here, output fed back to input. In that case, what's going to happen, you will have difference equations where there won't be only x of n minus n minus 2. There will be y of n minus 1, y of n minus 2, y of n minus 3, and so on. Okay. So it happens. Okay. So now, so that's about difference equations. Okay. So and how are these related to, how are these difference equations related to transfer functions? How are these related to transfer functions, by the way? Now, have you done this thing, by the way? I think you have done in your Shivanand sir class. Every differential equation you can apply the Laplace, right? For differential equations you apply the Laplace transform and you end up getting h of s, right? Similarly here, when you have the difference equation, you can see this is something similar. X of n with 1z, x of n minus 1, x of 1 more z to the power minus n, x of n minus 2, y of n. This is a feedback, y of n minus 1 multiplied by y of n minus 2 multiplied by a2. So these kind of difference equations, if at all you apply the z transform, what's going to happen? Y of n becomes y of z. A1 is A1 only, whether in time or frequency domain. A1 still remains A1, A2 remains. It's a linear system. Plus remains a plus, see, plus remains a plus. Okay, plus remains a plus. But if y of n is equal to gives you y of z, y of n minus 1 gives you z to the power minus 1 into y of z. Y of n minus 2 gives you z to the power minus 2 into y of z. Okay, so now what I will do is, just like the way you got transfer function h of s from the differential equation, here if at all you are given a circuit like this or a difference equation like this, I will take the transfer function of the entire thing. Then I will take the ratio y of z divided by x of z. That gives me my transfer function h of z. Now see here, I had this particular general circuit. Okay, so what did I do? I applied the Z transform. Using the linearity and the time shift property, and I get the ratio h of z, which is y of z divided by x of z. Hence, I have the transfer function. Hence, I have the transfer function. So let me conclude this by telling you that just like you had h of s for the continuous time systems with differential equations, for the discrete time systems, we have h of z. Okay. For discrete time equations with difference equations, we have the transfer function h of z. Okay. So what all things can we do, by the way? Why are you interested in the transfer function? You have studied transfer functions, you have studied in your control systems also. Here also, once again, you are studying transfer function for discrete time systems. Well, control systems, whatever you are studying there is mainly for continuous time system. Here we try to do something similar for the discrete time systems. Okay. Here we try to do something similar for the discrete time systems. Okay. By taking the z transform, the ratio of the z transform y of z by x of z. Okay. So what all things can we do here, by the way? Okay. So did you get this thing? You had the differential equation here. You had the differential equation here. You took the z transform. You got y of z the ratio outside, and there you have the h of z, the ratio y of z by x of z, getting you the transfer function. This is also transfer function, whereas HFS is also transfer function. This is for digital circuit. That was for analog circuits. Okay, that was for, and this is a generalized method. Okay, this, by the way, is a generalized method where you don't know the values, right? Some A and some B coefficients. Okay, what is thing? Now let us try to understand what can we do with it. What all things can we do with the transfer function? If at all you happen to know the transfer function, what all things can you do? Let us see. You are done. You are doing something similar in your control system also. So first thing you can do is you can determine the frequency response. You have done this thing in your Laplace transform also. Now I think you might have come to this particular chapter. If at all you have h of s, if at all I simply replace s by j omega, if at all I simply replace s by j omega, I get the frequency response where omega is the frequency, right? You remember what is meant by frequency response? Frequency response is this particular thing which you plotted for your what was that? Your RC coupled amplifier. Remember, RC coupled amplifier, you had plotted something like this, right? Based on input, you are trying to plot the response of the output. This is something similar. Frequency. How does the system behave for a particular frequency? Does it give a gain for a particular frequency? Does it give a loss for a particular frequency? How much is the gain for which frequency? Now, since your input is analog, you can do analysis for analog frequency omega. Now, since the moment you convert the data from x of t to x of n, then what you get is you get the z transform. And if at all you replace your z by e to the power j omega, if at all you replace s by j omega, you get the analog frequency response. If at all you replace z by e to the power j omega, you get the digital frequency response. Now, what is the difference between analog frequency and digital frequency? Let us see it, as and when the situation arises when we try to study the discrete time Fourier transform. Okay, so let me tell you once again. If at all you simply replace s by j omega, we get the continuous time Fourier transform. Okay. If at all I replace s by j omega, I will get continuous time Fourier transform. If at all I replace z by e to the power j omega in the digital transfer function, I will get discrete time. I will get discrete time Fourier transform. Remember this. Remember this. So because we are not covered with the transfer DTFT yet. Okay, we'll come to this chapter later. We'll study Fourier transform and DTFT. Let's, once we are comfortable with Laplace, which you have already studied, and once you are comfortable with Z, it's going to be much more easier. So what is the utility of the transfer function? It lets us determine the frequency response. Okay, that is one deal. So you get the transfer function, simply replace z by e to the power j omega. We get the digital frequency response. What all things can we do here, by the way, with it? Okay. Second thing what we can do is we can always predict the system properties. Okay, the stability, the causality, and all those things. So do you remember doing something like this here in your Laplace transform? I think in your Laplace, in your control system, you have studied this stability, Routh-Hurwitz criterion, right? You take the h of s, then you plot the poles. You tell that if the poles are there on the left side, then it is stable, poles on the right side, then it is unstable, and so, right? Similarly here for the Z transform, if at all you happen to know, if at all you happen on the transfer function, now using transfer function you can identify the poles, right? In your Laplace transform also, if at all you have h of s, then only you can identify the poles, right? Similarly in discrete functions system, if at all you happen to know h of z, then you can identify the poles. Now the rule is, if at all the pole lies inside the circle, if the pole lies inside the circle, then the system is stable. If the pole lies outside the circle, then the system may be unstable. A causal system, pole lies inside the circle, a causal system is stable. Pole lies outside the causal system is unstable. Got this thing, got this thing. So to be able to find the poles, you have to have the transfer function. Okay, that was that. Then moreover, what you can do is you can always implement the digital structures. What is this digital structure, by the way? Digital structure is this particular thing here, what you saw, right? These structures here, okay. You can always implement these particular structures. Now how did we do this particular things? How did we implement these digital structures here, by the way? So if at all you are given the transfer function, from those transfer functions you can always get the difference equation. From the difference equation you can get the digital structure. Isn't it easy, right? You go from the textbook to the notebook, then you have to go to the laboratory. It's very, very easy. Okay. So implementing the circuits is very easy if at all you happen to have the access to the transfer function. Okay, it lets you implement and lets you optimize the system. Okay, lets you implement and also lets you optimize the system also. Okay, so with this brief introduction to the transfer function, okay, so now I have done two things. I have related why transfer function analysis here, transform analysis, what we call. It lets us do what all things your Laplace transform allows you to do in the control systems for the continuous time system. We are trying to do something similar here for the discrete time systems using the Z transform. Okay, got this thing. Now let us get started. Okay, now let us get started. Okay. So here is an example. Here is a simple example. What is the topic supposed to be? The topic was supposed to be this here. Okay, I got. The topic is this. So first thing that we'll do here is we will relate the transfer function and the difference equation. Okay. So here what author is telling is, if at all we happen to have a difference equation, can we arrive at the transfer function? Can we? And if at all you happen to have the transfer function, can we arrive at the difference equation? Okay, so if somebody, some author has given us only the impulse response, right? If this happens usually, you will be getting, you have this black box, you don't know what does it do, right? You have this black box, you bought something from Chinese, right? The reverse engine sort of thing. You don't know what does it do. So what do? You simply give it an impulse. Assume, right? Assume. So you simply give it an impulse, you get the impulse response. Okay, from this impulse response, what you do is you take the Z transform of that impulse response, and then you get the transfer function. Okay, once you get the transfer function, then what you do is you get to write the difference equation, and once you write the difference equation, then nobody can stop you in implementing that particular circuit, right? Right. So the transfer function and difference equation are so related that if at all you happen to know the circuit, you can straight away go to the impulse response, and if at all you happen to know the impulse response, you can straight away go to the implementation also. Let us see an example. Let us see a simple example. Okay. Okay, so here is a simple thing. Here is a simple thing. What is it? What author is asking us here? Find the difference equation description of a system with the transfer function. Here, what author is done? Author is interested. Can we implement this particular thing? Right? You have done this thing, right? If at all you have been given an h of s, trying to get a differential equation from h of s. If at all you get the differential equation, you can straight away get the circuit. Okay. So differential equations of clever way of representing a circuit without actually drawing the messy circuit. Okay. Okay. So how do we do this thing, by the way? How do we do this thing? H of z equal to 5z plus 2. H of z equal to okay, divided by z square plus 3z plus 2. Okay. So first thing what we have to do is we have to make sure that the difference equation contains everything in terms of y of n and x of n and its previous values. There cannot be y of n plus 1. There cannot be reference to the future values x of n plus 2, y of n plus 3, because it indicates a non-causal system. Non-causal systems are practically impossible to implement in labs. That is why what we have to do is, but if at all you apply the property here, 5z indicates n plus 1. That is why it won't be fair. That is why what we have to do, first we have to represent the given transfer function in polynomials of z to the power minus n in terms of negative powers of z only. How do I do this? By the way, I simply divide the numerator and denominator by z square. Okay. Wasn't that easy? Yes. Now we do this. Now what we will do, I will equate this to y of z. I will equate this to y of z divided by x of z. I will equate this to y of z divided by x of z. So what's going to happen? This term here gets multiplied by x of z. Okay. So this term cross multiplication, right? It's a cross multiplication. This term gets multiplied by x of z. Now this y of z comes here. Okay. This term gets multiplied by y of z. This term gets multiplied by y of z. So what do we have here? So y of z plus 3z to the power minus 1 into y of z plus 2z to the power minus 2 into y of z. 1 into y of z. If at all I take the inverse, so what do I get? I get y of n. 3 into y of z. 3 remains a 3, right? It's a linear system. Constant remains a z to the power minus 1 into y of z. Z to the power minus 1. If y of z gives you y of n, z to the power minus 1 into y of z, the time shift property, it will give you y of n minus 1. 2 remains a 2. Z to the power minus 2 into y of z gives you y of n minus 2, right? Y of z multiplied by z to the power minus 2 because of the time shift property gives you y of n minus 2. Similarly, 5 remains a 5, 2 remains a 2. Constant remain constant. Right? It's a linear system. Plus remains a plus. X of z into z to the power minus 1 gives you y of n minus 1. Z to the power minus 2 into x of z gives you x of n minus 2. Okay. Okay. Got this particular thing? Now, did you get this thing, by the way? Now, did you get this thing? So here you are given a transfer function and they asked you to get the difference equation. So what did you do? The first thing you check whether it's in positive powers of z or negative powers of z. Somehow you converted into a proper fraction and you made sure that everything was in negative powers of z. Then what you did was you simply took the inverse z transform. You did the cross multiplication of this thing with y of z divided by x of z. Cross multiply y of z divided by x of z. Okay, there you have it. There you have it. So you got your difference equation. Okay, you got your difference equation. Okay. What all things can we do with this? What all things can we do? Author says we can predict stability and causality. Author says we can predict stability and causality. Okay, from the transfer function. Now, do you buy this argument? Stability and causality with the transfer function. Author says, here is an equation, poles and zero. Okay, of a causal system. He's telling. Okay, suppose the system is causal. Causal in the sense, what is meant by causal system? System where your impulse response is existing only on the right side or on the zero. Okay, for causal system, if the pole lies inside the circle, if the pole lies inside the unit circle, if the pole lies inside the unit circle, then okay, if pole lies inside the unit circle, then what happens? Then this remains a stable system. Okay, it means if at all the system is causal, if the system is if the system is causal, then if at all there is a pole which lies inside the unit circle, then the system is always stable. If the pole lies outside, then it is unstable. That means now if at all I take a example, h of z, h of z equal to, see what we are trying to do is we are trying to predict the stability. Okay, we are trying to predict the stability based on the transfer function. Okay, suppose I have z divided by z minus 2. Okay, h of z equal to z divided by z minus 2. Now say this system here, this transfer function, system represented by this transfer function. Now the question is, if this is causal, this is causal means what? Causal means right sided. What can be its impulse response? So this can be, this can have an impulse response, this can have an impulse response, h of n is equal to, this is can have impulse response, h of n is equal to what, 2 to the power n. Okay, 2 to the power n into u of n, right? This can have impulse response. This can also have another impulse response. What is that another impulse response? Minus 2 to the power n u of minus n minus 1, right? This can also have the impulse response minus 2 to the power n u of minus n minus 1, right? Minus 2 to the power n u of minus n minus 1. But then this one is right sided. Okay, this one is right sided. The second one here is left sided. The second one here is left sided. Now we are interested to know, author has given us, say this is right sided, causal. Is it stable? Is it stable? Now z divided by z minus 2, can you tell me, if at all I equate the denominator to 0, if at all I equate the denominator to 0, I will get a pole at 2, right? You equate the denominator to 0, you get the pole. You equate the numerator to 0, you get a 0. Okay. Now see here, now this particular thing, what is that property of ROC? ROC of a stable system includes a unit circle. That was one thing. And second thing here is, what author is telling is, if there is a pole inside unit circle, then the causal system is stable. Now see here, this pole here, is it inside of the unit circle? This is the unit circle. This is having a radius of 2. This is straight away outside. So that is why you can see 2 to the power n into u of n. It's a growing exponential, right? 2 to the power n into u of n is a growing exponential. So this can never be stable. Okay, this can never be stable. Whereas z divided by, if at all I have z minus 0.5, if at all I have in place of 2, if at all I have z divided by 0.5, if at all I have in place of this, if at all I have z minus 0.5, then what's going to happen? If at all I have z minus 0.5, then what's going to happen? I will get 0.5 to the power n into u of n, right? If that is the case, then I'll get h of n equal to, inverse that transform, 0.5 to the power n into 0.5 to the power n into u of n. 0.5 to the power n into u of n means, how does that look like? So now that is a straight away a decaying exponential, right? That is a decaying exponential. Now where does this pole lie? Z minus 0.5 equated to 0. The pole here lies inside the circle. Okay, so then the system is going to be stable. So what is the conclusion of the story here? So that means, if at all you happen to know the transfer function h of z, if at all you happen to know the transfer function h of z, and author says that this is a transfer function of a causal right-sided system. If it is so, then if there is a pole lying inside the circle, then the system is straight away stable. If there is a pole lying outside the circle of unit radius, then the thing is straight away unstable. Now what this thing? The entire stability, just like you had in the Laplace transform, the poles on the left side, LHP. Similarly, we have poles inside the circle. Okay, poles inside the circle give a stable and causal system, whereas poles outside the circle If the system is causal, it can never be stable. Okay. Okay, what the thing. So similarly, for a stable system, what is the rule for a stable system now? If the pole happens to be inside the circle, the system can be stable. If the pole lies outside the circle, then also the system can be stable, given that the system is left sided. Given that the system is left sided, that means this system is anti-causal. Okay, the system is non-causal in nature. It is going to the left side. Okay, it's going to the left side. It can be stable. It can be stable. Okay, see, z divided by z minus 2. Z divided by z minus 2 can be stable. It can be stable, but not this particular thing. Not if it exists on the right side. But if it exists on the left side, minus 2 to the power n u of minus n minus 1. This is stable. This is easily, this is stable. It starts at minus 1, then goes on decaying. This one is stable. Okay, so if you say the system is causal and if the pole lies inside the circle, then it is stable also. If you say the system is anti-causal, non-causal, left-sided, then if the pole lies outside the circle, then it is stable. Everybody is confused, right? Just see problem, maybe, then maybe it will be clear. Okay. Okay. So author concludes by telling that a system is both stable and causal if all its poles lie inside the unit circle in the z plane. Okay. So this is a requirement. All the poles should lie inside the circle for a system to be both stable and causal. Remember, causal system indicates that output depending on present and previous inputs and outputs, whereas non-causal system indicates that your terms it's going to contain is y of n plus 1, x of n plus 1, n plus 2, the future values, which is illogical. It exists in the notebooks only for analysis, but it doesn't make any sense. Okay. But this particular thing. Now let us concrete our study with this particular example. Here author is telling that this is straight away taken from Heikin. Okay, I had put it in Google Classroom also. You can download it. Okay, so what is it? Author has given a transfer function. Author has given us transfer function here. Okay, and he wants to know the impulse response from the transfer function. He simply wants to know the impulse response. How do you get the impulse response from the transfer function? How do you get the impulse from the response from the transfer function? You simply take the inverse z transform. Okay, you simply take inverse z transform, you get impulse response from transfer function. But what is the missing thing? What is the missing thing? If at all you want to get the inverse z transform, you need to be provided with ROC, right? Here, that is the tricky part. Here h of z is given, they wanted to find h of n, but they did not give the ROC. Okay, if z divided by z minus 2 is given. Okay, say if z divided by z minus 2 is given, if there's a ROC is magnitude z is greater than 2, then you understand this is 2 to the power n into of n. If they say ROC is magnitude z less than 2, then you understand that it's a left-sided sequence, right? So here the trick is they have not given the ROC. Instead, they say that you get me the impulse response if the system is stable or if the system is causal. Okay, will you try this thing? The answer is in the next page. The answer is in the next page. But then, can you just take a time of 1 minute? Now see here. This is in the form. This is a constant, 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 constant. This is in the form 1 divided by 1 minus alpha z to the power minus 1. Right? This is same as z divided by z minus alpha. Okay. It's the same as z divided by z minus alpha only. Only thing is numerator will be multiplied by a constant. Okay. So now, which is the alpha here? This term here you can see. This is my alpha. This one, and this one here you can see. So here in the first case, 1 divided 1 minus alpha to the power minus 1. Now what it can be? So there can be two types of results. So it can be alpha to the power n into u of n, or it can be minus alpha to the power n u of minus n minus 1. Okay. So now here, looking at these questions, what do you think this can be? First he says that it has to be stable. Okay. 2, okay, it's a constant 2. Now see here, now you tell me 0.9 to the power n into e to the power j pi by 4. E to the power j pi by 4. What is the magnitude of this? What is the magnitude of this? Magnitude of this is only 0.9, right? Now see, where does the pole lie? 1 divided by 1 minus alpha z to the power minus 1. This is equal to z divided by z divided by z minus 0.9, right? This is simple. Z divided by 0.9 into e to the power j pi by 4. Okay. That's what it is. Okay, pi by 4. That's what it is. So if the system is causal, if the system is stable, then if I develop this into a left-sided sequence, right-sided sequence, 0.9 is less than 1, right? So if at all it's a right-sided sequence, if at all this is a right-sided sequence, then it is going to be a decaying exponential. Why? Because 0.9 is less than 1. If at all I develop it into a left-sided equation, then what's going to happen? Minus 0.9 to the power e to the power j omega n u of minus n minus 1. Then it is going to give me a growing exponential on the left side. Okay, then it's going to give me growing exponential left side. That's why I will assume that this to be a right-sided sequence. So for this particular thing, minus 2 to the power n into u of n, if at all I keep it as a right-sided sequence, it give me a growing exponential on the right side, whereas if at all I develop it as a left-sided sequence, then it will give me a decaying exponential on the left side. So I will consider this as a right-sided, this as right-sided, and this as a left-sided sequence, and hence my conclusion is for this system to be a causal system, right-sided u of n, 2 to the alpha to the power into u of n, alpha to the power into u of n, minus 2 to the power u of minus n minus 1. Okay, let me stop here. Tomorrow we will continue.